I'm Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss the definitions and terminology related to the module 4, that is light and optics. And before going into the discussion, we will first try to understand what a definition is. The act of defining or of making something very definite, distinct and clear, we call it a definition. Or the formal statement of the meaning or the significance of a word or a phrase, idiom, as we find it in the dictionary. Or we can also say it is a statement expressing the essential nature of something. So when you have to express something, the essential nature of it, you are calling it as a definition. So whenever we try to write a definition, we have to use the proper terms and we have to define as it is. Now, why is it so important? Why is a definition so important? Because they enable us to have a common understanding of the subject. So when two people are talking about a common topic, if they are using the correct definition, then the understanding is very clear. And also they will allow all of us to be on the same page when we are discussing or reading about a issue. So therefore, we have to make sure that we properly define our words and phrases so that everyone will understand. Now coming to terminology. What is terminology? It is the body of terms that we use with a particular technical application in a subject of study or a profession. And what is the importance of this terminology? Why is it important to use the correct terminology? So terminology plays an important role in understanding the context and specialized texts. So when you are using a particular term, so in which context and which we are using it is very important. Also, understanding the intricate terminological details of the technical and scientific concepts helps students comprehend what the main message of the document is. Not only that, it will also help the specialists to transmit the content in a very effective manner. So therefore, we are always trying to understand what a definition is and how we are going to use the definition and terms in a given context. So let us come to the outline of the module 4. What we are going to discuss in this 1 hour session. We are going to discuss about definitions and terms related to Huygens principle, superposition of waves, terms which we are using in Engs double slit experiment, then also related to fringe width, Newton's rings, and then diffraction due to single slit, double slit, and also end slits. So these are the topics and the definitions and terminology we are going to discuss. So first we are going to see what is a wavefront or define a wavefront. A continuous locus of all the neighboring particles vibrating in the same phase. So what is important here is the neighboring particles and they all have to vibrate in the same phase. Now if you take the continuous locus of all such particles, you get a wavefront. So let us see how we are getting it. Now suppose there is a disturbance that is caused here. Now we are considering some particles. What we are considering? The neighboring particles. So all these are the blue dots are the neighboring particles to this disturbance. Now if these particles, all of them vibrate in the same phase means same state of vibration. Now the locus of this which connects all these particles gives us the wavefront. So this is the wavefront. So you understand we have a disturbance. We are considering the neighboring particles shown by blue dots and all these particles are vibrating in the same phase, then the locus of all these points, the continuous locus, gives the wavefront. So this is the wavefront. Now, when can light form a spherical wavefront? We are discussing about spherical wavefront. When light spreads from a point source, when the source of disturbance is a point source. In an isotropic medium, the light travels with the same velocity in all directions and arrives simultaneously at all points lying on a sphere. The same example we have seen. If you are having a point source and if you consider particles, neighboring particles like this, okay, these are all the neighboring particles that are vibrating. The medium here is isotropic. What do you mean by isotropic? Means the refractive index should remain uniform throughout that medium which we are considering. Then only the light waves will travel with the same velocity, because if the refractive index varies, then the velocity varies. So from this point, in all directions, if they are traveling with the same velocity, so they will arrive at points simultaneously lying on a sphere. Then that will give us a spherical wavefront. Now, if they are not traveling in this with the same velocity, then they may arrive at different points. So then we may not get a spherical wavefront. So what is important here is a point source, isotropic medium, so that the light waves will travel with the same velocity in all directions, and they have to arrive simultaneously at all points lying on a sphere. So this is what we have seen here. If you are talking about the point, now all these are coming at the same point simultaneously on a spherical surface. So we get a spherical wavefront. Now, when can light form a cylindrical wavefront? So we have already seen a spherical wavefront. So what is a cylindrical wavefront? So when the source of light is linear in all isotropic medium. So instead of taking a point source, we are taking a line source. Means this is the source of light. Means you imagine if you are considering a tube light. Okay. So the source there is linear. So whenever the source of light is linear, the wavefronts will take the cylindrical shape. So what you see here is the cylindrical shape. Whatever wavefronts that are transmitted in the forward direction, they will be cylindrical in shape. So you will call it as a cylindrical wavefront. Now, when can light form a plane wavefront? So we are talking about different types of wavefronts. So when is it a plane wavefront? If a point or a linear source is placed at infinity, if the source is at infinity, then the portion of spherical or cylindrical wavefront in a small region is a plane, and we will call it as plane wavefront. So for us, let us imagine the source is somewhere here and we are considering the wave at a very far off point, say at this point P. Very far, we are considering it as infinity. Now this point source will send out waves, the locus of all the points on which it has the same vibration. We are calling it as a wavefront. Now we consider a point source or a linear source. So for example, we have considered a point source. Now, if the wavefronts, if you are talking about, are like this, so as you go away, the wavefront may be like this. And if you take a part of it, see, a small region, if you are considering, is a plane. If you are considering a very small region, this appears to be plane. So clearly what it says is, when the source is at infinity, we are getting a plane wavefront. Now, define the principle of superposition of waves. What is the principle of superposition? So, when two or more waves act upon a particle or arrive at a point simultaneously, means at the same time, the resultant displacement of the particle is the algebraic sum. I can say vector sum also, because we will take the direction also into consideration. So sum of the displacements of the particle due to individual waves in the absence of the other. So let us try to understand this. So we are talking about two waves here. It can be two or more. So the simplest thing, let us see for two waves. So there are two waves that are arriving at a point simultaneously. So let us take two waves. So this is wave 1, whose displacement is denoted by y1. And this is wave 2, whose displacement is denoted by y2. And these two waves are arriving at a point simultaneously. You imagine they are coming at a point, this point simultaneously. Then what is the resultant displacement at that point due to these two waves? That is what we are trying to understand in principle of superposition. So the resultant will be the vector sum of the displacements of the particles due to the two waves, or due to the two individual waves in the absence of other. Means what is the displacement due to the first wave in the absence of the second one? What is the displacement of the second wave in the absence of the first one? So y1 and y2. So the resultant displacement y will now be y1 plus y2. I am taking y1 plus y2 because they are moving in the same direction. So y is equal to y1 plus y2, having the same state of vibration. So this is what gives us the principle of superposition. Next, define interference of light. What is interference? So when two light waves superimpose, the resultant amplitude in the region is the superposition, and the amplitude is different from the amplitude of the individual waves. So in the principle of superposition, what we have seen, the resultant displacement is the vector sum of the displacements due to the two waves. So the resultant now depends upon the vector sum of the displacements due to the two waves. So definitely the resultant amplitude is different from that of the individual waves. So this modification in the distribution of intensity in the region of superposition, we call it as interference. Means the intensity gets modified. If they are both in the same phase, we'll call it as y is equal to y1 plus y2. So the resultant is greater than the individual displacements. And if they are in opposite phase, we write it as y is equal to y1 minus y2. So depending upon the values of y1 and y2, it will be less than either of the one. So the modification of the distribution of intensity in the region of superposition, we are calling it as interference. Next, define Huygens principle of propagation of wavefront. So according to Huygens, how does the wave front or the wave propagate forward? Each point on the wavefront acts as a center of new disturbance. Each point acts as a center of new disturbance and emits its own set of spherical waves called secondary wavelets. And the envelope of all these wavelets in the forward direction gives the position of the new wavefront. So how we are getting the new wavefront, you see here. Suppose we have, this is the source, and because of the disturbance here, all these particles, neighboring particles are vibrating. And the locus of all these points, we are calling it as the wavefront. So this is the wavefront. We call it as old wavefront. Now, each point on this wavefront will act as a source now. So each point act as a center of new disturbance and emits its own set of spherical waves called secondary wavelets. So because of this, there is a wave. Because of this disturbance here, there is a wave, spherical wave that is moving. Because of this, we have this. Because of this, we have this. Now, if I take the locus of all these points, we get the new wave. So the envelope of these wavelets in the forward direction gives us the position of new wavefront. So how we get the new wavefront is according to Huygens principle. Now, how is the phase difference related to the path difference? So let us first understand what is path and path difference. Then what is phase and phase difference. Now, if I am talking about a wave, one complete wave we consider. Now, the total length travelled by this wave, we call it as the path. That is called as path. When I say path difference, now I am taking another wave. Now the path travelled by this wave may be different from this wave. So what is the difference in the path travelled by the two waves? We are calling it as path difference. Now what is phase? It talks about the state of vibration of the particle. Now if I am talking about a particle here, this particle is vibrating in the upward direction. When I talk about a particle here, it is vibrating in the downward direction. And when we complete one complete vibration, again the particle here will travel in the upward direction. Means we will start having another wave. These waves will keep on repeating. So now what I try to understand here is when the wavelength is lambda, for a complete wave, the length of a complete wave we call it as lambda. The phase difference is 2 pi. Means here also it is in the upward direction. Again 360 degrees it is rotating, again it is coming in the upward. So the difference is 2 pi. So for every lambda, the phase changes by 2 pi. So the phase difference is 2 pi by lambda times the path difference. Phase difference is 2 pi by lambda. How we are getting it is from here. For every lambda, it is changing by 2 pi. So for unit, I talk about, so 2 pi by lambda. So the phase difference will change by 2 pi by lambda times the path difference. Now define fringe width. So first let us see what is fringe and then the fringe width. So if you consider this experiment, we call it as Engs double slit experiment, where we are seeing two slits. This is slit S1 and this is slit S2. Now, these are the waves that are emitted from the first source and these are the waves emitted from the second source. Now, if you see, there is superimposition of these waves. So what we understand here is all the points where these particles arrive in phase, the waves arrive in phase, will have a bright fringe. Now means, I see here at the center point, whatever waves that arrive here and the superposition, it is all due to the constructive interference. So we get a bright fringe. Constructive interference means a crest falls on a crest. Okay, so we get a bright fringe. Now, whenever they interfere out of phase, we get a dark fringe. So this is a dark fringe. So the yellow ones are the bright fringes and the dark ones are the dark fringes. So we have a series of bright and dark. So bright, dark, and so on. And how we are numbering them? Suppose if m is equal to 0, this is the first central bright fringe. The next bright fringe is +1 in the upward direction. Next one is m is equal to +2. So these are the bright fringes. And how we are numbering the dark fringes? This is the dark fringe, m is equal to 0. Now this is m is equal to +1, dark fringe, m is equal to +2, dark fringe. Upward direction, we are taking it as positive. And in the downward direction, we take them as negative. -1, -2. Here also m is equal to 0, m is equal to -1. So this is how fringes are formed. Fringes means we are having alternate bright and dark fringes. Now what is fringe width? the spacing between any two consecutive bright or dark fringes. So I talk about this and this bright fringe. The spacing, I can say the distance between these 2 points. We will call it as fringe width. And you can take between any two dark also from here to here. That is the fringe width. So the fringe width is the spacing between any two consecutive bright fringes or dark. Or I can take it from here to here. So because they are equally spaced, so in an interference pattern, because they are equally spaced, the fringe width is the same between any two consecutive bright or dark fringes. We call it as fringe width. Now define coherent sources. Two sources are said to be coherent when the waves emitted by them have the same frequency and constant phase difference. Same frequency means the number of waves that are emitted per unit time should be the same. So if I am considering two sources, when do I say they are coherent? Means when they are emitting waves having the same frequency and the same phase difference. So they can be in phase, or the phase difference should be a constant phase difference. Then only we will say that the two sources are coherent. Now if you see the previous example, we have taken two sources. If these two sources are emitting waves of the same frequency and having constant wave difference, then we say S1 and S2 are coherent. Now, what is a Plano convex lens? Plano convex. So, a Plano convex lens is the one which has a positive focal length and has one spherical surface. This surface is spherical and this surface is flat or plane, I call. So, this is called a Plano convex lens. One side is plane or flat and the other side is spherical. So you will call it as Plano convex. So if you are taking a concave lens, it will be different. We are talking about convex lens. So we are writing it as focal length positive. Now define a convex lens. How do you define a convex lens? A convex lens is also known as converging lens. What is converging? Converging here means all the rays of light traveling parallel to the axis will converge at a point. So let us understand. We'll consider a convex lens. Okay, this is the principal axis. Principal axis passes through the optic center and also the principal focus. If this is F here, this is also F here. Now, a converging lens will converge all the rays of light traveling parallel to the principal axis. So, this is the principal axis for us now. What is the principal axis? A line that passes through the principal focus and the optic center. We call as a principal focus. Now, we will consider rays traveling parallel to the principal axis. So, these are the rays moving parallel to the principal axis. Now, these rays of light will converge. Okay, after passing through the lens, they will converge at a point. Therefore, you are calling it as converging lens. So, this is the principal focus where they may converge. So, we are calling it as converging lens. And a convex lens, if we are talking about a double convex, both the sides convex, it is relatively thick at the middle and thin at the upper and lower edges. So, if you see this here, it is thick at the middle but thin at the edges, upper and the lower. Now, if you see here, we are not discussing about a concave lens, but it is important to understand the difference. If we are talking about a concave lens, okay, a concave lens is always thin at the middle and thicker at the edges. So, this is how you can remember. So, this is a convex lens, convex on both the sides. This is concave. So here it is thick at the center and thin at the edges. Here it is thin at the center and broad at the edges. So that is the major difference between a convex lens and a concave lens. Now define radius of curvature. What is radius of curvature? Radius of curvature of a lens is the radius of the hollow sphere of glass of which the lens is a part. So from where we are getting the lens? So the radius of that particular sphere, we are calling it as radius of curvature. Let me give you the example. Suppose we consider a hollow sphere. So we are considering a hollow sphere. And out of it, we cut a lens and keep it. I will take out this part outside. Means I will take out this outside. This portion I have taken outside and kept it here. Now, what will be the radius of curvature of this lens? So, how do you get the radius of curvature? It is the radius of curvature of the hollow sphere. This radius of which this lens is a part. No, this is a part of it which we have taken outside, cut and kept it outside. So the radius of this spherical sphere of which this lens forms a part, we will call it as R. So I hope you understood. It is the radius of the hollow sphere of which the lens is a part. Now define focal length of a lens. What is focal length? Distance between the principal focus of a lens or a mirror. If you are considering a lens, it's a lens. For a mirror also you can take. Distance between principal focus and the optic center. So what is an optic center? The center of the lens, we call it as the optic center. And the point where all the rays will converge, we'll call it as the principal focus. So the distance between the principal focus and the optic center, we call it as focal length. The principal focus is always denoted by capital F and the focal length we denote by small f. Next, define Newton's rings. What are Newton's rings? So to define Newton's rings, let us first understand this Newton's rings setup, experimental setup. So once we understand this, then we'll be able to define the Newton's rings. So in this setup, what we have is a Plano convex lens. So if you see here, this is plane and this is convex. So we take a Plano convex lens and keep it on a plain glass plate, thick plain glass plate like this. This is a plain glass. So whenever you are placing a Plano convex lens on a thick glass plate, so what you see here is in the region between this Plano convex lens and the glass plate here, there is air. So there is an air film, I can say. There is an air film in this region and the thickness of this air film is not uniform. It is minimum at the point of contact and keeps on increasing towards the edges. Now, when this kind of setup is there, when light falls on this surface, at this point, some of the light will reflect, some will transmit, it will go through the air, and again it gets reflected from the other surface. Now, when these two rays interfere with each other, the ray 1 and the ray 2, when they interfere with each other, we get an interference pattern. And that interference pattern is in the form of rings, what you see here. Okay, you can see rings here. So the pattern is in the form of rings. And this was found by the scientist Newton. So we are calling them as Newton's rings. So it is a phenomena in which an interference pattern is created. How was the interference pattern created? By the reflection of light between two surfaces. One is a spherical surface and the other is an adjacent flat surface. So this is the spherical surface of the lens, convex lens, and this is the flat surface. So the two rays that are coming from these two surfaces, when they interfere, they give us an interference pattern. And the pattern is something like this. So this we are calling it as Newton's rings. Now give one example of Newton's rings. So in our day-to-day life, many places we see the Newton's rings. So one example is whatever you see, the colorful fluorescence on the water surface, when there is a thin layer of oil or kerosene on it. You see something like this on the road sometimes. Okay. So when there are potholes that are filled with water during the rainy season and vehicles move and there are oil dripping onto it, then what happens when oil falls on it? It forms a layer on the surface of water. And when light falls on it, there is reflection from the upper surface, curved surface, and the flat surface of the water. And when these two rays interfere with each other, you get something like Newton's rings. And you will see colorful films like this. You can see something like this, which you usually see on water on the roads, or on bubbles also you see the same kind of setup. So they are colorful. So this is one example of Newton's rings. Next question. Why is the center of the Newton's ring dark? So when we have seen the Newton's rings pattern, this is the Newton's rings pattern we have seen. This center position is dark. Then you have bright, dark, and so on. So whatever we are talking about, this dark color is the dark fringe. And this light color is the bright fringe. So what we have is alternate dark and bright fringes, we say, which we are calling them as Newton's rings. Now the question we are trying to understand is, why is this central fringe dark? Why it can't be a bright fringe? Because in the Engs double slit experiment, we have seen that the central fringe is a bright fringe. But here we are saying it is a dark fringe. Why is it dark? So at the center, the thickness of the air film formed between the lens and the glass plate is 0. It is obvious. When you see at this position, there is no air film. No, at the point of contact, exact point of the contact, there is no air film. So we are writing that the thickness of the air film is 0. Therefore, at the center, the geometrical path difference between the rays, incident and reflected from the glass plate is 0. But there is a path difference of lambda by 2 due to reflection, because the rays, when they are reflected, there is always a path difference of lambda by 2. So this path difference gives rise to destructive interference. So we have already seen whenever the path difference is an integral multiple of lambda, you have constructive interference. This is constructive interference. And constructive interference gives rise to bright fringe. This is giving rise to bright fringe. Now, when the path difference is an odd multiple of half the wavelength, so I can put it like this, 2n plus 1 into lambda by 2, where n takes on the values 0, 1, 2, 3 and so on. So when n is equal to 0, we have lambda by 2. When n is equal to 1, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2 and so on. So whenever it is a multiple of half the wavelength, that is lambda by 2, we have destructive interference. The interference is destructive and this gives rise to dark fringe. So with these two concepts, what we understand here, because there is a path difference of lambda by 2, which gives rise to destructive interference, so it is the center fringe is dark. So that is what we observe, that the central fringe is always dark here when we are seeing it in reflected light. Now the next one, explain Young's double slit experiment. So what is this Young's double slit experiment? So let us see the setup what we have here. we have a source which sends out light waves, and we are placing two slits S1 and S2 equidistant from the slit. Okay, only then these two slits will become coherent. They will become coherent sources. Means the distance traveled from here to here should be the same. So the light coming from this source will pass through these two slits. Now the waves that are emitted from S1 and S2, they will interfere with each other. So when they interfere, when they are interfering in phase, we get a bright fringe. This is the bright fringe. And when they are out of phase, we get a dark fringe. So on the screen, what we see is a series of bright and dark fringes. Bright, dark, and so on. The yellow ones denote the bright fringes, and in between it is dark. So what it shows here, it shows that light has both wave and particle nature. How you can understand this is, suppose if the light passes through the two slits and it has only particle nature, then what happens on the screen, we should see only a patch here and only a patch here, if at all light is a particle. But what we are seeing is a pattern, an interference pattern, a series of bright and dark fringes. That is possible only, or that can be explained only with the wave nature of light. So it shows that light has both wave nature as well as particle nature, and these natures are inseparable. That is what we are trying to understand. So light is said to have wave particle duality. So this is what we call as the dual nature of light. Rather than behaving only as a wave or only as a particle, it exhibits both a wave nature as well as particle nature. So the same is true for electrons and other quantum particles. So we are also discussing that electrons, they are particles, but still they exhibit wave nature. So the converse is also true. If light is a wave, it can exhibit particle nature. Then electrons, which are particle, they can exhibit wave nature. So this wave particle duality is applicable to radiation as well as particles. Now define constructive interference. What is constructive interference? When the resultant amplitude is the sum of the amplitudes due to the two light waves, then the interference is constructive interference. Means I'm taking two waves. This is the first wave having an amplitude y1. This is the second wave having an amplitude y2. And the resultant amplitude is the sum of the amplitudes. Means because these two are in phase. In phase means the state of vibration is the same. Wherever you have a crest, there is a crest. Wherever there is a trough, there is a trough. Means they are exactly in phase with each other. These two waves, I consider them to be in phase with each other. So now these two waves, when they arrive at a point simultaneously, so the resultant displacement here is the vector sum y1 plus y2. And this is maximum, or it is the sum of the two displacements. Then what you call it as constructive interference. Means they are in phase with each other. So we get constructive interference. And we have also seen the condition, the path difference can be n lambda. If there is no phase difference or they are in phase also, we have constructive. And whenever the path difference is an integral multiple of lambda, then also we have constructive interference. Now define destructive interference. How do you define destructive interference? If the resultant amplitude is equal to the difference of the two amplitudes. So when do you take the difference between the two? Now you see here, this is the wave whose displacement is y1, and this is the wave whose displacement is y2. Now if you see these two waves, so wherever you have a crest, you have a trough. So they are differing in phase by lambda by 2. What is the phase difference between them? it is pi, or the path difference is lambda by 2. So lambda by 2 is the path difference. So now if I have to write the resultant displacement here, y will be equal to y1 minus y2 because it is in the opposite direction. We are considering the vector sum or the difference of the two amplitudes. What is amplitude here? The displacement, the maximum displacement in any direction, you call it as amplitude. So this is the maximum displacement it can have. So y is equal to y1 minus y2. So because the amplitudes are the same, they cancel out. So what is the way we have is a null way. Here, what is the path difference? It is lambda by 2. So whenever the path difference is an odd multiple of half the wavelength, then you have destructive interference, and always destructive interference gives rise to dark fringes. Next, define diffraction. What is diffraction? Diffraction refers to various phenomena that occur when a wave encounters an obstacle or an opening. Or you can also define it as the bending of waves around the corners of an obstacle. So whenever light is traveling, if there is an obstacle in between and the size of the obstacle should be very small, we will discuss about it. In that case, what happens? Light will bend around the corners. You see in this example here, you have the light waves. So when these light waves are encountering the solid disk, which is very small in size, now the light rays are bending here at the corners of the obstacle. So the bending of the waves around the corners of the obstacle or through an aperture, you may have it as an aperture, not as an obstacle, into the region of geometrical shadow or of the aperture. Now if you see, you have an obstacle here. When light falls on it, what do you understand here is there will be an image of the object that is formed here. But what we are observing due to diffraction is these rays will bend into the region of this geometrical shadow. This is the geometrical shadow of this disk on the screen. This is the screen. So this is the geometrical shadow. If the rays are not bending, you will not see any pattern here. But because of this bending of the rays around the corners of the obstacle, what you will see here is a pattern in the geometrical shadow. So they are bending and they are coming into the region of the geometrical shadow. This is what we call it as diffraction. Now, on what factors does the amount of bending happens in light? Means whenever it encounters an obstacle, the size of the obstacle should be comparable with the wavelength of light. So the amount of bending depends upon the size of the obstacle and the wavelength of the wave. And whenever the size of the obstacle is comparable with the wavelength, only then we'll be able to see the diffraction pattern. Otherwise, you cannot see the diffraction pattern. Now, how did Fresnel give the reason for the diffraction phenomena to occur? Now, whenever we are talking about diffraction, we discuss two types of diffraction given by two different scientists. Fresnel is the name of the scientist, Fresnel's diffraction we call, and the other one is Fraunhofer diffraction. So we are in the next few minutes, we are going to discuss about these two types of diffraction, how these two are different. So we are now talking about Fresnel's diffraction. So according to Fresnel, diffraction phenomena is due to mutual interference of the secondary wavelets originating from various points of the same wavefront, which are not blocked off by the obstacle. So what he said is, if you have a source and there is an obstacle, we are taking it as an aperture here. Now, if there is mutual interference of the wavelets that are coming from different points on the wavefront, on the same wavefront, and they are not blocked by this obstacle, then you have Fresnel's diffraction. The pattern which you get, we call it as Fresnel diffraction. Now, how do we explain this Fresnel diffraction? The source and screen are at finite distances. Finite means which are measurable. So this is the source and this is the screen, and the distance between them is measurable. They are at measurable distances or finite distances, and no lenses are used for making the rays parallel. So we are not using any lenses here. Okay, and the incident wave is either spherical or cylindrical. You see here the waves that are incident here are shown by spherical wavefront. Now the next one is Fraunhofer diffraction. Fraunhofer is another scientist who gave a different pattern here. So the source and screen are placed at infinite distance from the aperture or the obstacle. So here if you see, the source is somewhere here at infinity, and the rays here, we are showing the source here. To bring these rays onto this obstacle, what we use is a lens. This is a lens. Only then we are getting this parallel rays. And the incident wavefront is a plane wavefront. That is a major difference. In Fresnel diffraction, the source and screen are at finite distances, but here they are at infinite distance. And there the incident wavefront is either spherical or cylindrical, but here it is a plane. We have seen that all the rays that are coming from infinite point, if the source is at infinity, we call it as a plane wavefront. Now state the major difference in phenomena of interference and diffraction. We have discussed two important phenomena. One is interference and one is diffraction. What is the major difference between the two? So first, in interference, it takes place between two separate wavefronts. So see in the first diagram here, we have a source S. Light from this source is allowed to pass through two slits S1 and S2. Now the waves that are coming from S1 and coming from S2, they are sending out, they act as coherent sources and send out waves. And the waves from S1 and S2, they are two different sources. Now they are interfering with each other, or I can say two separate wavefronts coming from two coherent sources. They interfere and we get the interference pattern, bright and dark fringes. That is what we get here in interference pattern. This is interference. Now in diffraction, what we are going to see, the interaction takes place between the secondary wavelets originating from different points of the same wavefront. So here we are not having two different wavefronts. We are having the superposition due to the secondary wavelets originating from different points on the same, this is the same wavefront, but we are considering different points on the same wavefront and the waves that are interfering, and you get a diffraction pattern. So this is diffraction. So what is the major difference here? So it is due to the interference of two separate wavefronts coming from two coherent sources. But in diffraction, it is from the secondary wavelets originating from two different points on the same wavefront. Now the next one is, what is diffraction grating? We have already seen what is diffraction, bending of the light around the corners of the obstacle. Now we are going to understand what is grating and then understand diffraction grating phenomenon. So diffraction grating is a component of optical device consisting of surface ruled with close equidistant parallel lines for the purpose of resolving the light into spectrum. So what you see here is, you take a transparent material, and on this transparent material, we draw lines with a very fine diamond point. These lines are very closely spaced. How closely spaced means we'll be drawing at least 15,000 lines per inch. In 1 inch, that is around 2.54 centimeters, we are going to draw 15,000 lines. For the purpose of understanding, we have shown them distinct, but otherwise they are very close lines. These are the ruled lines. How we are drawing the ruled lines? With the help of a diamond point. Why diamond point? Because it will be very precise, very sharp and fine. So on a transparent material, we are drawing lines. So when you draw the lines, what happens? Wherever there is a line, it becomes opaque. Means it will not allow the light to pass through. So this is a opaque one and this is also opaque. Now the region in between the two opaque lines is transparent and that acts as a slit through which light will pass. I hope you understand. So these two lines which we are drawing is opaque and the region between the two lines is transparent, which acts as a slit through which light will pass. Now the width of the slit we consider it as E plus D. Now what happens when light falls on this grating? Light will pass through these regions in between the two lines which act as slits. Now what is a plane transmission grating? If the ruled lines are opaque to light, while the space between the lines is transparent, then they act as a slit and it is known as transmission grating because it's able to transmit the light. We are calling it as transmission grating, a plane transmission grating. Now what is a plane reflection grating? We have seen what is a transmission grating. Now what is a plane reflection grating? If the lines are drawn on a silvered surface, here we have taken a plain transparent surface. If the surface is silvered, then what happens? Light gets reflected from the space between the lines. Whatever opaque lines we have drawn in between, there is a portion from which the light will get reflected. Then you will call it as plane reflection grating. Next, define path difference. So what is path difference? Path difference or PD is the difference in the distance travelled by the two waves from their respective sources to a given point on the screen. Let us try to understand it with the help of this diagram. So here we are having two slits or two sources, so A and B. Okay, so there are two waves. One wave coming from here to the point P, they are arriving at P, and another one coming from B, it is reaching P. Now, what is the path travelled by the ray coming from A? It is AP. And what is the path travelled by the ray coming from B? It is BP. So, these two are the paths travelled by AP, by the ray 1 coming from A, by the ray 2 coming from B. Now, path difference is the difference in distance travelled by the two waves. So, what will be the difference? If you see geometrically, you can see BP is more than AP. So, the path difference is the difference in the distance travelled by the two rays, BP minus AP. And they are coming at the same point on the screen. So, this is how we calculate the path difference. Now, define phase difference. We have seen path difference. So, what is phase difference? It is used to describe the difference in degrees or radians when two or more alternating quantities reach their maximum or zero values. So, I have explained it with the help of this figure. So, when the wave is starting from here, the complete wave, this is the zero position here. So, here the particles here and the particle here will be in phase with each other. Next, define angle of incidence. What is angle of incidence? So, to understand this angle of incidence, let me draw a simple diagram. This is a reflecting surface, I can say. I draw a normal to it. What is a normal? A line drawn at 90 degrees to the surface. We call it as normal. So, this is normal. Now, a ray of light is incident on the surface. So, I say this is PQ. What is PQ? PQ is the incident ray. PQ is incident. Now, the angle which the incident ray PQ makes with the normal, we call it as I. Angle PQ is the incident ray. This QN I can say is the normal. QN is the normal. This angle which the incident ray meets with the normal, we are calling it as angle of incidence. So I here is the angle of incidence. Angle of incidence. So how we are trying to understand in geometric optics, angle of incidence is the angle between a ray incident on the surface and the line perpendicular to the surface at the point of incidence, which is called the normal. So you can simply say the angle between the incident ray and the normal drawn at that point gives us the angle of incidence. Now what is angle of reflection? Angle between the reflected ray and the normal at the point of incidence. So if you have the surface, we have already discussed about this. This is the normal. If a ray of light is incident on this reflecting surface, so we have taken PQ as the incident ray, QN is the normal, and this is the angle of incidence. Now, this ray will reflect like this. Now, this angle we call it as R, the angle of reflection. So, the angle between the reflected ray, I will say QR here represents the reflected ray. QR is the reflected ray. So, the angle which this reflected ray QR makes with the normal, we are calling angle R as the angle of reflection. This is the angle of reflection. Now, define focal point. The point that all light rays from a mirror or a lens pass through. So, focal point is the point through which all the rays in case of a lens or a mirror will pass through. We will call it as the focal point. Now, when do you call that the two waves are in phase? When are they in phase? When the two or more light waves overlap exactly at the crest and the trough, then they are said to be in phase. So, if you see here, this is the first wave, crest, second wave, crest. First wave, trough, and the second wave, trough. So, they are exactly matching with each other, overlapping with each other. Then you say they are in phase. If crest coincides with the crest, trough coincides with the trough, for two or more, here we have shown only two waves. It can be more than two waves also, but when they are coinciding in such a way that the crest falls on crest and trough falls on trough, we say that they are in phase. And when do you say they are out of phase? When they overlap such that the trough of one wave overlap with the crest of the other. That is what you have to understand. Now, this is the first wave, crest. This is overlapping with the trough of the second wave. The trough of the first wave is overlapping with the crest of. So, when the trough overlaps with the crest, then they are out of phase. And we have seen the resultant is the resultant amplitude will be the difference between the two amplitudes we have already discussed. So, out of phase means crest on trough or trough on crest. Now, define a lens. We have already discussed about different types of lenses. A curved transparent object usually made up of glass or a clear plastic which is used to direct the light, that we are calling it as a lens. Now, define light. The basic question, what is light? Light is a form of energy which is traveling through the universe in the form of waves. And the wavelengths of the visible light range from around 4,000 angstrom to 7,000 angstroms. This is the wavelength of the visible light which we can see, a human can see. Now, define wavelength. What is wavelength? The physical distance that a light travels in one wave cycle. So, how do we show that? The physical distance means here, this is one wave. So, the physical distance the light travels in one wave cycle. So, this is one wave cycle. So, this distance we will call it as lambda, the wavelength. And all electromagnetic energy is transmitted in the form of waves. So when a wave is being transmitted, we calculate the distance traveled in terms of wavelength, lambda. Now define monochromatic light. Mono always represents single. Chromatic is always represented to color. So light of single color means single wavelength. Each color has a particular wavelength. So whenever we are talking about a source, we consider a monochromatic source of light. So what is monochromatic source of light means? We have light of single wavelength or single optical frequency. And we know that the wavelength and the frequency are related using the formula V is equal to n lambda. So when the wavelength differs, the frequency also differs. So monochromatic light contains light of single optical frequency. So we'll stop here. Thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.